All right, in this next video we're going to look at the second case we've seen where we have complex eigenvalues. So we have a linear system and its eigenvalues are complex. All right, now what we've seen in our previous work is that we don't need to use both. This is where this case is a little different than the first one, where we don't need to use both the eigenvalues, the a plus bi and a minus bi. We only need to use the one with the plus sign, and via Euler's formula, that's going to help us determine two linearly independent solutions to our system. Okay, and just remember what Euler's formula was. I'm just going to write that out, right? So it's e to the I theta, all right, is equal to cosine of theta plus I sine of theta. All right, so if we're using e to the a plus bit, and we have to distribute the t through the parentheses here, we get e to the at plus I and then bt, and then again we had what we've done before is split that up as a product, e to the at times e to the I times bt. All right, and I just wanted to remind you of that because that shows why the bt part is the only part showing up inside the sine and the cosine down below here. All right, so different than case one in that we get complex eigenvalues, similar in the sense that we're still going to look at this expression e to the lambda 1t times our fixed eigenvector v. All right, so we're assuming we have some eigenvector v corresponding to the eigenvalue, in this case the complex eigenvalue a plus bi, and then we apply Euler's formula to the e to the lambda t part. That gives us what I'm underlining here in black, e to the at times cosine bt plus I sine t times our fixed eigenvalue. And then after multiplying all of this out, all right, so we could multiply the e to the at part and the I sine, or e to the at sine bt part in through the expression here into the eigenvector, the constant eigenvector. That's going to lead us to end up getting and decomposing it as a function of t, a real valued vector function of t, and plus I times another real valued function of t. All right, and this is where the complex case is interesting. So we can build the general solution of that by essentially throwing away the I. It turns out that W1 and W2, the real parts and the imaginary parts, which are real vector valued functions, are actually solutions to the original system, and that allows us to write the general solution down as a linear combination of those two solutions, W1 and W2. Okay, and again, there's no I in that formula. This is a real vector valued function that will solve our system, assuming it has complex eigenvalues. All right, and again, I'm playing up this idea about looking at the components of our vector valued function solution. All right, the components in this case, it's going to be e to the at cosine of bt times numbers plus and minus e to the at sine of bt plus or minus numbers. So again, linear combinations, sums of scalar multiples of exponentials times cosines and exponentials times sine functions. The long run behavior of our function, therefore, is going to be completely determined by the e to the at part, and therefore by the real part of the complex eigenvalue, which is a. All right, now we're looking at our possibilities here. Well, if a is equal to 0, then e to the at would be e to the 0 times t, which would be e to the 0, which would be 1, and we would get cosines and sines only in our components. And therefore, we have what we call a center equilibrium solution, meaning the graph is going to be of our, unless we're at the origin, the graph of our solution is going to cycle around the origin. Its graph is either going to lie on a circle or an ellipse. All right, it's going to go clockwise or counterclockwise around the origin. If a is positive, then what are we going to have? E to the at is going to approach infinity as t approaches infinity. All right, and in that case, our graph is going to, multiplying those by the sines and the cosines, is going to make our graph spiral away from the origin as t gets bigger, spiral towards the origin as t goes to negative infinity. So in this case, we call the origin, the only equilibrium solution, again in this case, is the origin, and we would say the origin's a spiral source. The last possibility is if the real part of our eigenvalue a plus bi is negative. In this case, e to the at is going to represent exponential decay, and that's going to approach 0 as t approaches infinity. And therefore we call the origin a spiral sink. The graph is going to spiral because we're multiplying exponentials times sines and cosines. All right, but it's going to approach 0 because the exponential decay is going to kill everything off. It's going to make everything approach 0. All right, again, this is an important thing to point out. The components are all going to be linear combinations of e to the at cosine bt and e to the at sine of bt. Keeping in mind what our eigenvalue was here, right? Lambda, for this case, was a plus bi. All right, so a, the real part of the complex eigenvalue, is the coefficient of t and the exponent of e, and b is the component of the coefficient of t inside sine and cosine. All right, so let's take a look at an example in this case. All right, so we've got a system here. On the left, written in component form. On the right, written in matrix form. It's an initial value problem also. We have an initial condition along with it. It turns out the eigenvalue for this system is, the eigenvalues are 1 plus or minus 4i. All right, and we only need to use the one with the plus sign. I got a little typo here. This should have been a plus, so we're only going to use 1 plus 4i. It's not that we couldn't use 1 minus 4i, but we only need 1 plus 4i, all right, to accomplish our goal, which is, in this case, writing down a general solution, using that general solution to help us solve this initial value problem in the example. All right, it can also be shown that a corresponding eigenvector to this eigenvalue, 1 plus 4i, is the vector 1i. All right, now what's a little bit more complicated about this than case 1 is we got complex numbers, all right, as our eigenvalue and as our components inside of our corresponding non-zero eigenvector. One thing that is consistent, though, is that we are going to write down e to the lambda t times v. All right, now what I've done here is I've got some of the steps written out there. We're going to expand it out. Okay, so we're going to get v, which is 1i, e to the lambda t, well, lambda is 1 plus 4i, so in the next step, what I've done is combine a couple things together. We're distributing the t through there. All right, so let's write a little bit of that work off on the side. That will be e to the t times e to the I 4t. All right, and then using Euler's formula, that would be e to the t times cosine of 4t plus I times sine of 4t. And then in this next step, I've distributed the e to the t through the parentheses here to get the next line. All right, now I've also done one other thing in that the vector 1i, I want to split that up as it's kind of into real and imaginary parts. And the way we can do that is realize that it's 1 plus 0i in the first component, 0 plus 1i. Oops, sorry, jumped up on me there. Just erase that. Okay, where was I? 1i in the second component. All right, and that will allow us to, in the third step here, to express it as 1, 0 plus I times 0, 1. All right, and now what we're going to do is we're going to multiply this out. And when we multiply the I term in the first parentheses by the vector with the I attached to it in the second parentheses, we have to take use of the fact that I squared is negative 1. So we're going to get a negative sign, and that negative sign showing up right here, I'll circle it, all right, in the first vector. All right, when we multiply out the other way, we multiply the inside and outside terms, all of those terms are going to have an I attached to it, and that's why the I is showing up in the front there. But once again, this is allowing us to detach from this and call W1 the real part, call W2 of t the vector valued function, which is the imaginary part. Again, no I, just the part inside the vector, and those are each real vector valued solutions. and therefore our general solution is a sum of scalar multiples of those. Notice they are linearly independent, because if I plug in 0 to the first one, we would get the fixed vector 1, 0. If I plug 0 into W2, we would get, in this case, the vector 0, 1. Right? So it's the standard basis vectors, actually. So those are certainly, along the x and the y-axis, those are certainly linearly independent, and therefore we can build the general solution as a sum of scalar multiples of W1 and W2. All right? Now, there's our general solution. Got that here. Start. All right, so it's K1 times W1 plus K2 times W2. Notice we've got constants K1 and K2, but the components individually are going to be sums of scalar multiples of e to the t times cosine or sine of 4t. Now, the initial conditions for this system, if we go back to this example, were 1 or negative 1, 1 when t was equal 0. Okay, so just doing a little bit of that work, we would set negative 1, 1 equal to what we would get by plugging in 0 for t, and we would get 1, 0 plus K2 times plugging 0 in for t above here. In the general solution we have starred there, we would get 0, 1. All right, and that readily gives us the constants K1 and K2 come out to negative 1 and 1 in this example. So now what I'm doing in the next step is just substituting in K1 and K2 as what they are, and then combining those vectors together. Okay, so in the next step down below here, we're just going to multiply the negative 1 to each component. Multiplying 1 in the second vector by each component doesn't change anything, but it allows us to write the solution to this system down as one single vector. We've got the x component function, the first one, and the y component function, y of t function, is the second component. And notice there also are linear combinations of exponentials and trig functions. In our case, it's e to the t cosine of 4t and e to the t sine of 4t, because, once again, our eigenvalue was 1 plus 4i. That single eigenvalue and its corresponding eigenvector helped us to determine the general solution, we wrote down above, and that will help us, therefore, to solve any initial value problem for this particular system that we're looking at. All right, now, what's going to happen to these functions? Well, we've got exponential growth with the e to the t, so this was not going to be a sink. It's going to be, in this case, a spiral source. I've got the solution graphed in blue here. Notice it passes through the point negative 1, 1, excuse me, which is about right here, when t is equal 0. So that's the point corresponding to t is equal to 0. All right, so we see we've got a spiral source. The origin for this system is, again, the only equilibrium solution. But this is a spiral source. The graph goes away from the origin, away from the equilibrium solution, as t goes to infinity. So we can see it's actually going to go out kind of to the right, going clockwise, as t goes to negative infinity. If we were, or to positive infinity, if we went backwards in time, we would go to 0. All right, so let's just write that out. So for our system, that we have the solution written down for above, if t goes to infinity, then this limit does not exist. I'll just say dne for does not exist. However, if we went the other direction, if we went to t equals negative infinity, then this one actually does go in towards the origin, or towards the 0 vector. That's it for this video.